Good morning, everyone. My name is Ruchita and I am from CSC AIML Section C. My subject name is Matrices and Calculus. Topic is Solving Integral Equations in Thermal Radiation Heat Transfer. Introduction to Thermal Radiation Heat Transfer. Thermal radiation is one of the three basic models of heat transfer. Alongside conduction and convection, it involves energy emitted by matter due to its temperature and travels in the form of electromagnetic waves. Integral equations play a central role in predicting radiative interactions between surfaces and participating media. Accurate modeling of radiation is crucial in high temperature systems such as furnaces, combustion chambers, spacecraft, and solar energy devices. Basic concepts of radiative heat transfer. Blackbody radiation, idealized emitter described by Planck's law, real surface deviate from this. Emissivity and indicate absorptivity indicate how effectively surfaces emit and absorb radiation. View factors, configuration factors quantify how much energy leaving one surface reaches another. Participating media, gases or particles that absorb, emit, or scatter radiation. Radiative transfer depends strongly on temperature to the fourth T power 4, making non-linear analysis essential. The role of integral equations in radiative transfer. Radiative heat exchange is fundamentally a spatial integration process because surfaces and media interact over distances. Integral equations model the contributions of emission, absorption, scattering, and reflection within a system. They account for geometry dependent interactions that cannot be captured by simple algebraic models, serve as the mathematical framework behind radiative transfer equations RTE and surface to surface radiation models. Types of integral equations in radiation. Surface integral equation used for gray or diffuse surface exchanging radiation in an enclosure. Volume integral equations needed when radiation occurs in participating media such as combustion gases. Fredholm integral equations for the first kind, typically ill-posed, arise when intensity at boundaries must be determined. Fredholm integral equations of a second kind, more stable, common in many radiation boundary problems. Volatile type integration equations appear in time dependent radiative transfer. Formulating the integral equation. Start from energy conservation of radiative transfer laws for surfaces. Use radiosity and irradiation relationship. For media, derive the integral form of the radiative transfer equations. Include effects such as incident radiation angle, spectral dependence, gray versus non-gray behavior, geometry via view factors or optical path lengths, scattering phase functions for part- particulate media. The resulting equations typically involve unknown such as surface radiosity or intensity distribution. Approximations and simplifications. Gray approximations assumes surface properties are wavelength independent, diffuse surface, simplicity, directional dependencies. Optically thin for optically thick media, reduce complexity of the RTE. Isothermal layers remove temperature variation terms such as approximation, trade accuracy for analytical or computational tractability. Analytical solution methods. Analytical solutions are limited to simple geometries or simplified media. Common approaches include separation of variables for symmetrical systems, integral transform methods, Laplace Fourier series expansions using spherical harmonics or legendary polynomials, exact view factor integration for classical exclosure problems. Analytical methods providing insights and benchmarks for validating numerical models. Numerical solution techniques necessary for complex geometries, non-gray surfaces, and participating media. Popular numerical frameworks include finite difference methods FDM, finite volume methods FVM. Once FVM, often used for RTE discretization, infinite elements method FEM, useful for complex domains. Numerical methods convert integral equations into algebraic systems that have been solved computationally. Discretization of integral equations. Domain is divided into elements, surface, patches, control volumes are nodes. Integral expressions are approximated using numerical quadrature, results in a matrix system typically linking radiosities or intensities across the mesh. Accuracy depends on mesh refinement, order of the quadrate scheme, treatment of angular description, example or discrete ordinates. Methods of moments in thermal radiation. Me- Methods of moments MOM transforms integral equations into matrix equations by expanding unknown in basis functions, commonly used for solving surface radiation problems with complex boundaries. Advantages: good accuracy with fewer unknowns, suitable for coupled radiation conducting or radiation fluid cases, requires careful selection on basis and testing functions for best results. Iterative solution approach. Large radiative systems often lead to a non-linear or dense matrix equations. Interactive methods include Gauss-Seidel, conjugate gradient, successive substitution for radiosity irradiation models useful for handling temperature dependent emissionally and absorption. Monte Carlo methods in radiative transfer. Statical methods that stimulate photon trajectories, extremely flexible for complex geometries, spectral radiation, participating media with scattering advantages, easy to implement and highly accurate drawbacks. Computationally expensive results have inherent static noise. Validation and verification of solutions. Verification ensured the numerical method solved the equations correctly. Grid refinement studies code benchmarking. Validation confirms the model representation. Physical reliability, compare with experimental measurements, use analytical solutions and reference cases. Importance to assume uncertainty and sensitivity in radiative calculations. Applications in engineering. Combustion system modeling flame radiation and heat transfer in furnaces, spacecraft thermal control, solar energy systems, high temperature materials processing, building engineering, predicting radiative heat exchange in vacuum, absorption and emission in collectors and receivers, glass, metals, ceramics, radiation in HVAC simulations and energy efficient design. Challenges and future directions. Accurately, modeling of non-gray media remains computationally demanding. Need for faster, high fidelity solvers are coupled. Increased use of machine learning to approximate radiate solutions, GPU accelerate for Monte Carlo methods, advanced spectra models. Future research aims to achieve real-time radiative heat transfer predictions for industry. Summary of key points. Integral equations form the mathematical foundations of radiative heat transfer modeling. Analytical solutions exist only for simplified cases. Numerical methods dominate modern research. Techniques such as MOM, validation, and verification are critical for ensuring reliable solutions. References and future readings. Models MF radiative heat transfer, Siegel and Howell thermal radiation heat transfer, thermal radiation heat transfer, 6th ED, Ingropera and DeWitt Fundamentals of Heat and Master. Recent journal articles explore advancements, numerical techniques, and applications. Conclusion. Solving integral equations is vital for understanding and optimizing thermal radiation transfer. Advances in computational methods continue to expand our capabilities in this field. Thank you.